across the rust-colored dust of Mars, where Earth appears as nothing more than a pale blue star in the twilight sky, humanity's greatest achievement stands silently in the cold. A collection of habitats, life support systems, and brave souls who have traveled farther than any explorer in history. They have planted flags, conducted experiments, and sent messages home declaring victory over the impossible. Yet within these pressurized walls, invisible cracks are already forming, not in the metal or composite materials, but in the delicate web of systems, resources, and human endurance that separates survival from catastrophe. Tonight, we explore a possibility that mission planners whisper about, but rarely speak aloud. What if the first Mars colony, humanity's boldest venture into the cosmos, could last only 100 days? 100 days, roughly 3 months, the length of a summer vacation, the time it takes for a season to change on Earth. It seems impossibly short for a mission planned over decades, built with billions of dollars, and staffed by the most capable humans our species can produce. Yet when we examine the cascading vulnerabilities of Mars colonization, when we trace the invisible threads connecting dust storms to life support failures, isolation to decision-making, and radiation exposure to equipment degradation, a troubling pattern emerges. The first colony might not fail from a single catastrophic event, but from a series of small, interconnected breakdowns that accelerate beyond anyone's ability to stop them. This is not a story of incompetence or poor planning. It is a story about the profound difference between visiting a world and living on one, about the gap between simulation and reality, between theoretical models and the unforgiving physics of a planet that has never sustained complex life. Mars does not merely challenge human engineering. It tests the fundamental assumptions we have made about survival itself. Assumptions built over millennia of living on a world with breathable air, protective magnetosphere, and ecosystems that recycle our waste into resources. The promise of Mars has always been intoxicating. A new world where humanity can start fresh, where we can become a multi-planetary species, where the lessons learned might one day carry us to the stars themselves. Yet the path between promise and reality is littered with variables we cannot fully predict until we are already there, committed, with Earth now a distant memory, and rescue measured not in hours but in years. What happens when the Martian environment proves more hostile than our most pessimistic models? When human psychology bends in ways no simulation could capture? When the machinery we depend on for every breath begins failing faster than we can repair it? Over the next journey together, we will walk through those 100 days, not as distant observers, but as witnesses to each critical moment. We will feel the dust that infiltrates every seal, taste the recycled air growing stale, measure the radiation accumulating in human tissue, and watch as isolation transforms trained astronauts into something else entirely. We will understand why food production might fail, why backup systems might cascade into simultaneous breakdowns, and why the final days might force choices that no mission planner ever wanted to consider. This is not merely speculation. It is an exploration, grounded in the realities of Martian conditions, the limits of current technology, and the patterns observed in extreme isolation studies here on Earth. It is a thought experiment that asks not whether we should go to Mars, but whether we truly understand what we are attempting when we do. Before we begin our countdown, I invite you to pause for just a moment, Comment below and let us know where you are watching from, what time it is in your corner of the world. Are you drifting off to sleep in Sydney, waking up in Stockholm, taking a quiet moment in Sao Paulo? This journey spans the globe, and knowing you are out there, sharing this exploration across time zones and continents, reminds us that curiosity knows no borders. Now, settle in. Let your mind drift across the millions of miles to that cold red world, and let us trace together the fragile thread between triumph and tragedy. Let us begin the countdown. Before we begin counting down the days, we must understand what makes Mars different. Not just different from Earth, but different from every challenge humanity has ever faced. Mars is not Antarctica, with its research stations enduring the polar winter. It is not the International Space Station where resupply missions arrive every few months. It is not the depths of the ocean where submarines descend knowing the surface waits above. Mars is something else entirely. It is a world that does not want us there, and every moment spent on its surface is a negotiation with forces that have remained unchanged for billions of years. On Earth, we are cradled by invisible guardians. The atmosphere wraps around us like a protective blanket, thick with nitrogen and oxygen, maintaining pressures that allow our blood to remain liquid, our lungs to draw breath without conscious effort. We do not think about this gift, we simply breathe. Above the atmosphere, Earth's magnetosphere stretches outward, deflecting the solar wind, the relentless stream of charged particles that pours from the sun at speeds exceeding 1,000,000 miles per hour. Without this magnetic shield, solar radiation would strip away our atmosphere, sterilize the surface, and render complex life impossible. Yet we rarely acknowledge it. It simply exists, working tirelessly, asking nothing in return. Water moves through Earth's systems in an endless cycle. Rain falls, rivers flow, oceans evaporate, clouds form. The cycle sustains forests, fills aquifers, moderates temperatures, and creates the conditions for life to flourish in nearly every environment. Temperature extremes are buffered by oceans and atmospheric circulation. Even in the harshest deserts or the coldest tundra, Earth maintains a delicate balance, a planetary thermostat fine-tuned over 4 billion years. We are born into this equilibrium, and it shapes everything we know about survival. Mars offers none of these comforts. The Martian atmosphere is not a blanket, but a whisper. At less than 1% the density of Earth's atmosphere, it provides almost no protection from radiation, no meaningful pressure to keep liquids stable, no oxygen to sustain metabolism. Standing on Mars without a pressure suit, human blood would begin to boil at body temperature within seconds. The lungs would collapse. Consciousness would fade in less than 15 seconds. Death would follow shortly after. The atmosphere that remains is 95% carbon dioxide, a thin veil of gas that cannot be breathed, cannot sustain fire, and offers only the faintest friction against incoming meteorites. Most burn up in Earth's atmosphere as shooting stars. On Mars, they strike the ground. Mars has no magnetosphere. Billions of years ago, its molten core cooled and solidified, shutting down the dynamo that once generated a protective magnetic field. Without it, the solar wind has spent eons stripping away the Martian atmosphere, grain by grain, molecule by molecule. What remains today is a ghost of what once was. Radiation pours onto the surface unimpeded. Cosmic rays, high-energy particles from distant supernovae, penetrate the thin air and bombard the ground. Solar flares send waves of radiation that would be lethal to unprotected humans within hours. On Earth, we receive about 0.1 rads of background radiation per year. On Mars, colonists would absorb that much every few days. The dust on Mars is not like sand on a beach. It is fine, electrostatically charged, and clings to everything. It infiltrates seals, clogs filters, coats solar panels, and reduces their efficiency. Martian dust storms can engulf the entire planet, lasting weeks or months, turning day into twilight and plunging temperatures even lower. The dust contains perchlorates, toxic compounds that, if ingested or inhaled, can damage the thyroid and disrupt human metabolism. Every surface touched, every tool used, every habitat entered becomes a potential contamination event. There is no rain to wash it away, no wind strong enough to clear it completely. The dust is patient. It waits. Temperature on Mars swings wildly. At the equator during summer, midday temperatures might reach a tolerable 70 degrees, almost comfortable by Earth standards. But as the sun sets, temperatures plummet to 100 degrees or lower. The thin atmosphere cannot retain heat. Thermal energy radiates into space almost instantly. Materials expand and contract with these temperature cycles, causing stress fractures, seal failures, and equipment degradation. Nothing on Mars experiences stability. Everything endures constant thermal shock. And then there is the distance. Mars, at its closest approach to Earth, is still 34 million miles away. During opposition, when the planets are on opposite sides of the Sun, that distance stretches to 140 million miles. Communication signals traveling at the speed of light take between 4 and 24 minutes to cross that void one way. A question asked on Mars receives an answer from Earth after an 8 to 48-minute delay. There are no real-time conversations, no immediate assistance, no emergency rescue missions. If something goes catastrophically wrong, help is not hours away. It is years away. The colonists are alone in a way no human has ever been alone before. This is why Earth analogues fail to prepare us. Antarctica is harsh, but it has breathable air, atmospheric pressure, and if disaster strikes, evacuation is possible within days. The International Space Station orbits in the relative safety of Earth's magnetosphere, with resupply missions launched regularly and emergency return vehicles always docked. Submarines operate knowing that surfacing is an option, that radio contact with the fleet remains intact. These environments test human endurance, yes, but they do not replicate the totality of isolation, the absolute dependency on artificial life support, and the psychological weight of knowing that Earth is not just distant, but unreachable. On Mars, every system must function flawlessly, continuously, without fail. Oxygen generation, water recycling, temperature control, power supply, food production, radiation shielding, waste management, and countless other processes must operate in perfect coordination. But here is the insidious truth. Systems do not fail in isolation. They cascade. A dust storm reduces solar panel efficiency. Power output drops. Heating systems are rationed. Internal temperatures fall. Condensation forms on cold surfaces. Water accumulates where it should not. Electronics short circuit. A pressure seal fails. Oxygen levels drop. Carbon dioxide scrubbers work harder, consuming more power. The cycle accelerates. One failure triggers another, and another, each compounding the stress on the remaining systems until the entire infrastructure teeters on the edge of collapse. This is the cascading failure problem, and it is unique to environments where redundancy is limited and resupply is impossible. On Earth, We are accustomed to external safety nets, emergency services, supply chains, natural resources. On Mars, there is no fallback. The colony is a closed loop, a fragile bubble of Earth-like conditions maintained by machines, by human ingenuity, and by the hope that nothing critical breaks at the wrong moment. The first 100 days are the most critical period for any Mars colony. This is the window when systems are new, but unproven, when human error is most likely, when psychological stress begins to accumulate but has not yet been fully understood or managed. It is the period when the colonists are still learning to live on Mars, still discovering which assumptions from Earth no longer apply, still adapting to the reality that survival is not guaranteed but earned, day by day, hour by hour. If the colony survives these first 100 days, it has a chance. If it does not, the dream ends. What follows is not speculation, but an exploration of the forces that could unravel that dream. Each phase of the 100-day countdown examines a different challenge, a different breaking point, and the cascading consequences that follow. These are not distant theoretical problems. They are the realities that any Mars colony will face, and understanding them is the first step toward ensuring that the fragile dream of life on another world does not shatter before it has truly begun. The first Martian sunrise over the colony is breathtaking. Amber light filters through the thin atmosphere, casting long shadows across the rusty plains. The habitat modules gleam with human achievement, their white and silver surfaces unmarked, pristine. The crew gathers at the observation window, watching dust devils dance across the horizon like spirits welcoming them to a new world. Everything seems possible, everything feels new. But within hours, they notice something peculiar, a fine coating on the solar panels, a residual glow clinging to the equipment after sunset. The dust has already arrived, though they have barely moved through it. Mars dust is not like Earth dust. It does not settle gently into corners or wait patiently to be swept away. It is everywhere, instantly, invisibly, as if the planet itself is made not of rock, but of powder that refuses to rest. Martian dust is a substance unlike anything encountered on Earth. Each particle measures between 1 and 3 micrometers, roughly 1/50th the width of a human hair. These microscopic fragments are the product of billions of years of weathering, ground down by temperature extremes and oxidized by ancient chemical reactions. Under a microscope, they appear jagged, angular, like tiny shards of broken glass, but their size and shape are only part of what makes them dangerous. What the first colonists discover, perhaps on day 3 or 4, is that Martian dust carries an electric charge. In the thin, dry atmosphere, dust particles become electrostatically activated. They cling to everything: spacesuits, airlocks, equipment surfaces, human skin. When crew members return from surface excursions, the dust doesn't simply brush off. It adheres with stubborn persistence, drawn by static forces that make removal nearly impossible. Even vacuum systems designed specifically for dust mitigation prove less effective than models predicted. The dust seems almost alive in its determination to remain. By the end of the first week, the accumulation is undeniable. Solar panels that were pristine at landing are now coated with a translucent film that reduces power output by 12%, then 15%, then 18%. Engineers projected regular cleaning cycles would maintain 90% efficiency. But the cleaning mechanisms themselves are fouled by the same dust they are designed to remove. Brushes become clogged. Compressed air systems push dust deeper into crevices rather than clearing it away. Each cleaning cycle becomes less effective than the last. The rovers that came before, Spirit, Opportunity, Curiosity, and Perseverance, all documented this phenomenon across years of operation. Solar-powered rovers experienced declining power generation that eventually determined their operational lifespans. Dust storms would sometimes clean panels by chance, dust devils sweeping across surfaces in fortuitous patterns. But such natural cleaning events cannot be predicted or relied upon. For a human colony depending on consistent power generation, the degradation curve is not just inconvenient, it is existential. Around day 10, the first health symptoms appear. One crew member develops a persistent cough. Another complains of throat irritation that will not subside. The medical officer runs tests and discovers trace amounts of Martian dust in nasal passages, despite rigorous decontamination protocols. The dust has infiltrated the habitat. This is when they learn about perchlorates. Martian soil contains between 0.5% and 1% perchlorate salts, chemicals used on Earth as rocket fuel oxidizers and in industrial processes. Perchlorates are toxic to human thyroid function and potentially carcinogenic. They were detected by the Phoenix lander in 2008 and confirmed by subsequent missions. Scientists knew they were present in the soil. What no one could fully predict was how easily they would become airborne, how readily they would be tracked inside, how impossible it would be to keep them out of human lungs. The habitat's air filtration systems are robust, designed to military specifications with multiple redundancies. Yet Martian dust is so fine that it penetrates standard filters with disturbing efficiency. HEPA filters rated to capture 99.97% of Earth particles struggle with the angular, electrostatically charged Martian variants. Filters begin clogging faster than replacement schedules anticipated. Changing filters becomes a twice-weekly ritual instead of a monthly one, consuming supplies at 4 times the projected rate. By day 15, mechanical systems begin showing signs of distress. The primary airlock door, cycled dozens of times daily, develops a grinding sound. Investigation reveals dust infiltrating the seal mechanisms, acting as an abrasive compound that wears down synthetic rubber gaskets designed to last 5 years. The joints on the robotic assembly arm outside the habitat move with increasing resistance. Dust has penetrated the protective bellows and is grinding against precision surfaces never intended to touch anything harder than lubricant. On Earth, dust is often soft, organic particles mixed with textile fibers and dead skin cells. Martian dust is purely mineral, composed largely of iron oxides, silicates, and volcanic glass fragments. It is essentially grinding compound, the substance mechanics use to polish metal. Now it is inside every moving part, every seal, every bearing. Engineers disassemble a failed valve on day 17 and find that dust has formed a paste with the lubricant, transforming smooth gliding surfaces into rough scored channels. The maintenance log grows longer each day. What was projected as 2 hours of daily maintenance becomes 4, then 6. Tasks that should take 30 minutes stretch to 2 hours, as crew members must first clean, then repair, then clean again. Every repair creates new opportunities for dust exposure. Every surface excursion brings more contamination inside. The habitat begins to feel less like a home and more like a fortress under siege by an enemy that cannot be locked out. One crew member, an engineer with experience in mining operations, makes an observation that haunts the evening debriefing. On Earth, she says quietly, dust accumulation is linear. You clean it, and it's gone for a while. Here, it's exponential. Every particle we track in attracts more particles. Every surface we clean becomes sticky with static and collects faster than before. We're not keeping up. We're falling behind. The psychological weight of this realization is profound. They are 18 days into a mission planned for years. Their supplies are calculated for months. Their resolve was forged through years of training. Yet the dust, something so prosaic it barely warranted concern during mission planning, is revealing itself as perhaps the most persistent challenge they face. By day 20, solar power generation has dropped to 74% of landing capacity. 3 critical seals require replacement. The backup air filtration system has been activated because the primary system is undergoing emergency maintenance. The medical officer has prescribed anti-inflammatory medication to half the crew for respiratory irritation, and the dust continues to arrive with every breath of the thin Martian wind, with every sunrise, with every footstep outside. The dust does not rage like a storm. It does not announce itself with fury or spectacle. It simply accumulates, grain by grain, particle by particle, inevitable as entropy itself. In the quiet moments between tasks, crew members find themselves staring at the fine red powder coating their equipment, their suits, their hands. This is not the Mars of exploration narratives. This is Mars as it truly is, a world that does not welcome visitors, but rather tests them grain by grain, measuring their endurance in micrometers of mineral dust that refuses to be conquered, contained, or controlled. The first 20 days teach a lesson that will define everything that follows. Mars is patient, Mars is persistent, and Mars is made of dust that will not rest. As the colony enters its 4th week, the dust has begun to settle, literally and metaphorically. The initial chaos of landing and setup has given way to routine. Systems hum with mechanical regularity. Solar panels collect the thin Martian sunlight. Water extractors pull moisture from the regolith. For a brief moment, it might seem that humanity has achieved what once existed only in science fiction, a foothold on another world. But inside the habitat modules, something invisible is changing. The air itself is beginning to betray the colonists. Life support systems represent perhaps the most complex engineering challenge ever attempted in human spaceflight. On Earth, we take for granted that the atmosphere simply exists, a gift of billions of years of planetary evolution, maintained by vast oceans, endless forests, and geological processes operating at continental scales. On Mars, every breath must be manufactured, monitored, and meticulously maintained by machines that cannot afford to fail even once. Consider what it means to breathe in a closed system. Each human exhales roughly 200 milliliters of carbon dioxide with every breath. Over the course of a day, a single person produces about 1 kilogram of CO2. In a small habitat with 6 colonists, that's 6 kilograms daily, over 40 kilograms per week. This invisible waste accumulates like water filling a sealed tank. Without removal, carbon dioxide levels would rise from Earth's normal 0.04% to dangerous concentrations within hours, not days. The technology designed to prevent this is called a carbon dioxide scrubber, and it is far more delicate than its industrial name suggests. Most advanced systems use a process involving chemical reactions with lithium hydroxide or molecular sieves that capture CO2 molecules as air passes through. These systems must operate continuously, without pause, in an environment where dust infiltrates every seal, where temperature fluctuations stress metal components, and where replacement parts exist only in limited storage. By day 21, the first scrubber begins showing anomalies. Efficiency drops by 3%, a seemingly small number, but in a closed system, small numbers compound. The backup scrubber activates automatically, but now there is no backup to the backup. The margin for error has vanished. Carbon dioxide is known as the silent killer, not because it cannot be detected, but because it creeps upward so gradually that the symptoms mimic exhaustion from normal work. At 1% concentration, colonists might feel slightly drowsy, attributing it to the demanding physical labor of establishing infrastructure. At 2%, headaches begin, persistent and throbbing, along with increased heart rate and difficulty concentrating. By 3%, cognitive function deteriorates noticeably. Decision-making becomes impaired precisely when clear thinking is most critical. The insidious nature of CO2 poisoning is that it doesn't announce itself with dramatic symptoms. There are no alarms in the body, no pain signaling danger. Instead, there is only a gradual fog descending over consciousness, a subtle theft of clarity that could lead to fatal errors in judgment. Yet carbon dioxide is only one piece of the atmospheric puzzle. Oxygen generation on Mars relies primarily on electrolysis, the process of splitting water molecules into hydrogen and oxygen using electrical current. It sounds elegantly simple in theory. In practice, it is a system with countless failure points. The water must be pure, free of minerals that would corrode electrodes. The electrical supply must remain constant. The electrodes themselves degrade over time, their efficiency slowly declining with each cycle of operation. Around day 28, power fluctuations from a solar array partially obscured by dust cause the primary oxygen generator to shut down unexpectedly. It restarts, but the incident reveals a deeper problem. The electrolysis membranes have been operating at higher temperatures than designed, accelerated by the need to compensate for the failing CO2 scrubbers. Materials that were rated for 5 years of operation may now last only 5 months. The backup oxygen system comes online, but it too relies on the same fundamental chemistry, the same vulnerable components. There is also a small emergency supply of compressed oxygen, enough for perhaps 3 days if rationed carefully. 3 days to solve a problem that might require parts that take 3 years to arrive from Earth. Meanwhile, another invisible threat emerges from an unexpected source: humidity. Humans are surprisingly wet creatures. Through respiration and perspiration, each person releases approximately 2 liters of water vapor into the air daily. In an Earth-sized atmosphere, this moisture disperses harmlessly. In a habitat module, it concentrates. The environmental control system must maintain precise humidity levels, a delicate balance between opposing dangers. Too much humidity, and water begins condensing on cool surfaces: walls, equipment panels, the inner surfaces of windows looking out at the rust-red landscape. This condensation creates the perfect environment for mold and bacteria, microorganisms that travelled from Earth as invisible stowaways. Some molds release spores that trigger allergic reactions or respiratory problems. Others produce mycotoxins that can cause serious illness. In the closed environment of a spacecraft or habitat, Mold is not merely unpleasant, it is a biological hazard that can compromise both equipment and human health. Too little humidity, and the colonists suffer from chronically dry mucous membranes, increasing susceptibility to infections. Nosebleeds become common. Static electricity builds to shocking levels, potentially damaging sensitive electronics. Eyes burn and itch. The discomfort is constant and wearing. By day 33, a musty smell begins permeating one section of the habitat. Investigation reveals dark spots growing behind an equipment panel. Mold, thriving in condensation, the environmental system failed to prevent. The contaminated area must be cleaned with precious water and disinfectants. But the incident raises troubling questions about what might be growing in spaces that cannot be easily inspected. Perhaps most concerning of all is a phenomenon that spaceflight engineers discovered decades ago, but still struggle to fully control: trace contaminant accumulation. Every material brought to Mars, plastics, fabrics, adhesives, electronic components, even the colonists' clothing, slowly releases molecules into the air through a process called outgassing. On Earth, these trace chemicals disperse into the vast atmosphere or are broken down by natural processes. In a sealed habitat, they accumulate day by day, breath by breath. Some outgassed chemicals are benign. Others are toxic at surprisingly low concentrations. Formaldehyde from insulation materials, volatile organic compounds from plastics, solvents from adhesives used in equipment assembly. Each individual compound might exist at levels measured in parts per billion, but together they create a chemical cocktail that has never been fully tested for long-term human exposure. The lesson came most dramatically during the Skylab missions of the 1970s. When astronauts first entered America's space station, they were overwhelmed by an unexpectedly pungent odor, later identified as hundreds of different chemicals outgassing from materials throughout the station. Some crew members experienced headaches and irritation. The problem diminished over time as the most volatile compounds dispersed, but it revealed a troubling truth. Even in facilities designed with the utmost care, the atmosphere of a closed system holds surprises. On Mars, atmospheric surprises cannot be ventilated away by opening a window. The external environment offers no relief, only near vacuum and temperatures that would freeze human tissue in seconds. Any contaminant released into the habitat air will remain there until actively removed by filtration systems that may themselves be struggling under the accumulated stress of Martian operations. By day 40, the Colonies' atmospheric monitoring systems show readings that hover at the edge of acceptable ranges. Carbon dioxide levels fluctuate between safe and concerning. Oxygen concentrations occasionally dip below optimal. Humidity swings from too dry to too moist as the environmental controls struggle to maintain equilibrium. Trace contaminant levels climb slowly but steadily upward. Emergency protocols exist, of course. Additional scrubber cartridges can be installed, though each use depletes irreplaceable supplies. Oxygen generation can be supplemented by chemical systems that produce oxygen through reactions with stored chemicals. But these too are finite resources. The habitat can be partially depressurized and repressurized using oxygen from emergency tanks, effectively flushing some contaminants, though this process consumes oxygen that cannot easily be replaced. These measures buy time, hours, perhaps days, but they do not solve the fundamental problem. The colony's life support system is operating at the edge of its design limits, and it has been doing so for less than 6 weeks. In the quiet moments between crises, when alarms have temporarily silenced and systems have stabilized into an uneasy equilibrium, the colonists might pause and consider a sobering reality. They are entirely dependent on machines to provide something humans have never before had to think about: the air itself. Every breath is an act of faith in engineering, and that faith is beginning to show cracks. By day 41, the colony has adapted to the dust. The air filtration systems have been modified, recalibrated, pushed to their limits. The crew moves with measured efficiency through their routines, conserving oxygen, conserving energy, conserving hope. Outside the habitat windows, the Martian landscape stretches in endless rust-colored silence. But something invisible has already begun its work. Something that cannot be filtered, cannot be avoided, and cannot be seen until it is too late. Radiation on Mars is not a theoretical danger. It is a constant, relentless presence. Unlike Earth, Mars has no magnetic field to deflect the charged particles streaming through space. No protective bubble shields this world from the cosmic bombardment that has poured down upon its surface for billions of years. Earth's magnetosphere is a gift we rarely acknowledge, an invisible guardian that redirects solar wind and cosmic rays away from our atmosphere. Mars lost its magnetic field long ago, perhaps 3.5 billion years in the past, when its core cooled and solidified. What remains is a planet exposed, vulnerable, bathed in radiation levels that would be unthinkable on Earth. The Martian atmosphere, thin as a whisper, offers little protection. At just 1% the density of Earth's atmosphere, it cannot absorb or scatter the high-energy particles that arrive from deep space. On Earth, our thick blanket of air stops most cosmic rays before they reach the surface. On Mars, they penetrate directly to the ground, passing through habitat walls, through equipment, through human tissue with quiet, invisible violence. There are two primary threats, and understanding the difference between them is crucial. Galactic cosmic rays arrive constantly, streaming in from supernovae and stellar explosions across the galaxy. These particles, protons and heavier ions, travel at nearly the speed of light. They are always present, always penetrating, a steady background hum of radiation that accumulates dose by dose, day by day. The human body aboard the Mars colony receives radiation exposure roughly 700 times greater than on Earth's surface. Not occasionally, continuously. Then there are solar particle events, sudden eruptions from the sun that can release torrents of charged particles in bursts of terrifying intensity. These storms are unpredictable. They can arrive with little warning, sometimes within hours of the initial solar flare. On Earth, we are shielded. On Mars, a solar particle event is a deadly phenomenon, a wave of radiation that can deliver lethal doses in minutes to anyone caught unprotected on the surface. The habitat was designed with radiation shielding. Engineers calculated the necessary thickness of walls, the protective properties of Martian regolith piled atop the modules, the redundancy of shielded sleeping quarters where crew could retreat during solar storms. The models were elegant, the simulations reassuring. But models are built on assumptions, and Mars has a way of exposing every assumption as optimistic. By day 45, a solar storm arrives. The Sun, 140 million miles away, erupts with a coronal mass ejection that sends a shockwave of particles racing outward. The Colonies monitoring systems detect the flare, triggering alarms throughout the habitat. The crew has practiced this drill dozens of times. They move quickly to the central sleeping module, the most heavily shielded section of the base, where layers of water tanks and regolith barriers offer the greatest protection. But protection is relative. Even within the shelter, radiation levels spike dramatically. Instruments measure the rise in dose, numbers climbing on screens that glow in the dim emergency lighting. Outside, the invisible storm rages. Particles slam into the Martian surface, into the habitat walls, penetrating aluminum and composite materials as though they were tissue paper. The shielding reduces the exposure, certainly, but it does not eliminate it. The crew huddles in the shelter for 18 hours while the storm passes, emerging afterward to check equipment and assess damage. It is 3 days later when the first symptoms appear. One of the crew members, a geologist who had been outside in a rover during the storm's initial phase, begins to feel nauseated. She dismisses it at first as stress, as the lingering effects of dust inhalation, as anything but what it actually is. But by day 52, the symptoms have progressed. Fatigue sets in, deep and unshakable. Her skin develops a strange redness, almost like sunburn, though no sun has touched her directly. Blood tests reveal what the medical officer had feared. Her white blood cell count is dropping. Acute radiation syndrome. The term is clinical, but the reality is visceral. Radiation damage occurs at the cellular level, disrupting DNA, destroying the body's ability to repair itself. The immune system, which relies on rapidly dividing cells, is particularly vulnerable. Red blood cells begin to fail. The body's capacity to fight infection diminishes. Nausea gives way to vomiting. Exhaustion becomes debilitating. And the medical equipment available in the colony, sophisticated as it is, was designed for emergencies of a different kind. Broken bones, lacerations, infections, these could be treated. But radiation sickness requires transfusions, bone marrow stimulants, isolation facilities to prevent infection in an immunocompromised patient. Resources the colony simply does not have in sufficient quantity. The crew realizes, with growing dread, that they are witnessing not just one case, but the beginning of a pattern. Others begin to report symptoms. Headaches that will not subside. Dizziness, a metallic taste that lingers in the mouth. These are the early signs of cellular damage accumulating faster than the body can repair. The long-term effects they had been warned about, the cancers that might develop after years of exposure, are manifesting in weeks. Mars is not following Earth's timelines. Part of the problem lies in the Martian regolith itself. The rust-coloured soil that covers the planet was supposed to serve as effective shielding when piled atop habitats. In theory, several meters of regolith would absorb incoming radiation, reducing exposure to manageable levels. But the regolith on Mars is not uniform. It contains iron oxides, perchlorates, and fine dust particles that, when struck by high-energy cosmic rays, can actually produce secondary radiation through a process called spallation. Incoming particles collide with atomic nuclei in the soil, fragmenting them and creating showers of additional particles, some of which are more biologically damaging than the original cosmic rays. The shielding is there, tons of it, laboriously piled and sculpted around the habitat modules. But it is not performing as the models predicted. The radiation environment is more complex, more penetrating, more persistent than anticipated. Dose rates inside the habitat remain elevated, and there is no escape. Every breath, every meal, Every moment of sleep occurs under a rain of particles that the human body was never designed to withstand. By day 58, the medical bay has become a makeshift ward. 2 crew members are bedridden, their bodies struggling to maintain basic functions. The medical officer rations the few doses of radiation countermeasures available, anti-nausea medications, compounds that stimulate blood cell production. But these are temporary measures, buying time rather than curing the underlying damage. The crew discusses options in hushed tones. Should they reduce time spent in less shielded areas? Should they abandon certain sections of the base entirely? Should someone attempt the journey back to Earth, knowing the radiation exposure during the months-long return trip would likely prove fatal? The invisible killer does not announce itself with drama. There are no explosions, no alarms, no visible threats. Just numbers on dosimeters that climb steadily upward. Just cells that stop dividing properly. Just immune systems that quietly collapse. Radiation is patient. It does not need to destroy the colony in a single catastrophic event. It simply waits, accumulating dose by dose, knowing that time itself is a weapon on a planet without a magnetic shield. As day 60 approaches, the crew understands that they are engaged in a battle they cannot win through determination alone. The radiation environment of Mars is not a challenge to be overcome with better technology or smarter planning. It is a fundamental condition of this world, as intrinsic to Mars as its red soil and thin air. They are living in a place where the universe itself is hostile, where invisible particles from dying stars across the galaxy pass through their bodies every second of every day, and no amount of shielding, no depth of shelter can fully stop what has already begun. By the 61st day, the Mars colony has survived dust storms, equipment failures, and the constant threat of radiation. The habitat still stands. The air recyclers still hum. But something far more subtle has begun to fracture. Something that cannot be sealed with tape or repaired with spare parts. The human mind, evolved over millions of years in the forests and savannas of Earth, was never designed for this. On Mars, isolation is not just physical, it is temporal, it is cosmic. And by the 3rd month, the weight of that isolation begins to settle into the bones of every colonist, transforming optimism into something darker, something that whispers that Earth is no longer home, but a memory fading into the void. The overview effect is a phenomenon experienced by astronauts who gaze upon Earth from space. They describe a profound shift in perspective, a sudden understanding of humanity's fragility and interconnectedness. Borders vanish. Conflicts seem trivial. The blue marble of Earth becomes a symbol of unity, suspended in darkness. But on Mars, there is no overview effect. There is only its opposite, a reverse revelation that strips away comfort rather than bestowing it. From the surface of Mars, Earth is not a blue marble. It is a pale blue dot, barely distinguishable from a star. Through a telescope, it might appear as a tiny crescent, sharing the sky with the moon, both reduced to pinpricks of light in the eternal Martian dusk. The colonists stare at this distant point and struggle to comprehend that everything they have ever known, every person they have ever loved, every forest, ocean, and mountain exists within that single pixel of light. The effect is not transcendence, it is abandonment. The mind cannot reconcile the vastness of the separation. Home becomes abstract, a theoretical place that may as well exist in another universe. Some astronauts who have experienced this describe a profound sense of derealization, a feeling that Earth itself might be imaginary, that perhaps they have always been here, drifting in the rust-colored emptiness, and memories of blue skies are nothing more than dreams conjured to ease the loneliness. Communication with Earth becomes a cruel reminder of the distance. Every message sent from Mars takes between 4 and 24 minutes to reach Earth, depending on the planet's positions in their orbits. Every reply takes just as long. A simple conversation becomes a day-long ordeal. How are you feeling? Takes 20 minutes to arrive. I'm struggling. Takes 20 minutes to return. By the time Mission Control responds with support, the crisis has either passed or deepened into something unrecognizable. This delay is not just inconvenient. It is psychologically devastating. Humans are social creatures who rely on immediate feedback, on the subtle cues of conversation, the rhythm of dialogue, the comfort of being heard. On Mars, there is no dialogue. There are only monologues cast into the void, followed by replies that arrive too late to matter. Colonists begin to feel that Earth has moved on without them, that their families are speaking to ghosts, that they themselves are already dead, separated from the living world by an insurmountable barrier of time and space. Inside the habitat, relationships that once held the crew together begin to fracture. In the early days, everyone was united by purpose and adrenaline. But by day 61, the novelty has evaporated. What remains are 6 or 8 people trapped in a space no larger than a small house, breathing recycled air, eating the same meals, hearing the same voices, day after day, with no escape, no privacy, and no end in sight. Personality conflicts that seem trivial on Earth become existential crises on Mars. A crewmate who chews too loudly becomes unbearable. Someone who organizes supplies differently triggers arguments that last for hours. Small habits, quirks of speech, even the sound of breathing can ignite disproportionate rage. Psychological studies of Antarctic winter overcruise and submarine missions reveal a phenomenon called long eye, where individuals avoid eye contact with specific crewmates for weeks, sometimes months, as a coping mechanism to prevent violent confrontation. On Mars, there is no rotation schedule, no relief crew arriving after 6 months. The same faces, the same confined space, stretching toward a horizon measured not in weeks, but in years. And as stress accumulates, decision-making deteriorates. Leaders who were once rational become erratic. Crew members withdraw into silence or lash out unpredictably. Trust, the invisible foundation of any team, begins to crumble. This is where the third quarter phenomenon emerges. It is one of the most well-documented psychological effects in long-duration missions, yet it remains one of the least understood. During expeditions that last months or years, crews reliably experience a collapse in morale roughly 3/4 of the way through. Not at the beginning, when challenges are fresh and spirits are high. Not at the end, when hope returns with the promise of completion. But in the interminable middle, when the mission is too far gone to turn back and too distant from the finish to see relief. On Mars, the third quarter phenomenon arrives around day 65. Suddenly, colonists who were once motivated lose interest in their tasks. Maintenance schedules are ignored. Scientific experiments are abandoned. Some crew members sleep excessively, retreating into unconsciousness for 12, 14, 16 hours a day. Others develop insomnia, lying awake in their bunks, staring at the ceiling, counting the seconds until a return to Earth that may never come. The psychological term for this is learned helplessness, a condition where individuals exposed to uncontrollable stressors eventually stop trying to change their circumstances, even when opportunities for improvement arise. On Mars, this manifests as a quiet surrender. The colonists know the mission plan. They know the resupply schedule. They know that survival depends on constant vigilance, but they no longer care. The future has become too abstract to motivate action in the present. Sleep, which should offer respite, becomes another source of torment. Mars rotates on its axis once every 24 hours and 39 minutes, creating a Martian day, or sol, that is slightly longer than an Earth day. 39 minutes may seem trivial, but to the human circadian rhythm, finely tuned by millions of years of evolution to Earth's 24-hour cycle, it is catastrophic. The colonists' internal clocks drift out of sync with the Martian day. They fall asleep later each night, wake groggier each morning, and soon find themselves in a perpetual state of jet lag that never resolves. Studies conducted on Earth using simulated Martian schedules reveal severe disruptions in sleep architecture. REM sleep, the phase critical for emotional regulation and memory consolidation, becomes fragmented. Deep sleep, necessary for physical recovery, decreases. After weeks on a Martian schedule, subjects exhibit cognitive impairments equivalent to severe sleep deprivation, heightened anxiety, depression, and in some cases, hallucinations. On Mars, where precision and clear thinking are matters of life and death, these impairments are catastrophic. A colonist miscalculates oxygen reserves. Another forgets to seal an airlock properly. Decisions that once took seconds now require minutes of foggy deliberation. And in the back of everyone's mind is the knowledge that a single mistake, one moment of confusion born from exhaustion, could end everything. Depression settles over the colony like Martian dust. It is pervasive, inescapable, and suffocating. Some colonists lose the ability to experience joy. They look at the Martian landscape, once awe-inspiring, and see only lifeless desolation. They think of Earth and feel not longing, but a hollow ache, as though the capacity for love itself has atrophied in the cold. Antarctica offers a troubling parallel. Winter over syndrome, documented among scientists stationed at polar research bases, describes a constellation of symptoms remarkably similar to what might unfold on Mars. Emotional blunting, irritability, insomnia, cognitive impairment, and in rare cases, acute psychosis. Unlike Antarctica, however, Mars offers no rescue, no helicopter evacuation, no early departure. The colonists are locked in, bound by orbital mechanics and fuel limitations, forced to endure until the return window opens, if it opens at all. By day 75, the colony has not failed mechanically. The systems function, the habitat stands. But inside, something essential has broken. The crew moves through their routines like automatons, hollow-eyed and silent, each person trapped within the prison of their own unraveling mind. They are not just isolated from Earth. They are isolated from themselves, from the people they once were, from any belief that meaning can be found in this red wasteland. The question is no longer whether they can survive the remaining 25 days. The question is whether, even if they do, there will be anything left of them worth saving. On day 76, the colonists conduct their weekly inventory with the same ritual precision they have maintained since arrival, but this time the numbers tell a story that can no longer be ignored. The food reserves are not merely low, they are critically insufficient. What was planned to sustain 12 people for 18 months will barely last another 3 weeks at current consumption rates. The margin for survival, already razor thin, has begun to collapse. The agricultural modules were meant to be the colony's lifeline, transforming Mars into a garden suspended in the void. Rows of wheat, lettuce, and potatoes growing under LED lights, their roots anchored in hydroponic solutions, carefully calibrated to provide every nutrient that Martian soil cannot. On Earth, the prototypes flourished. Scientists celebrated yields that exceeded expectations. But Mars is not a laboratory, and the agricultural challenge here reveals itself as something far more treacherous than anyone predicted. The first problem emerged quietly, almost imperceptibly. The plants grew, yes, but slower than Earth models suggested. Martian gravity, at just 38% of Earth's, affects more than human bodies. It influences how water moves through plant tissue, how nutrients are absorbed, how cells divide and expand. The wheat stalks are shorter, their grain production reduced by nearly a third. The lettuce grows pale and thin, its leaves lacking the robust structure they would have on Earth. Each harvest yields less than anticipated, and with every crop cycle, the deficit compounds. Then there is the matter of light. The sun on Mars provides only 43% of the illumination that reaches Earth's surface. The LED arrays compensate, bathing the plants in artificial daylight, calibrated to optimize photosynthesis. But electricity is finite, rationed among life support, heating, communications, and 100 other critical systems. When power reserves dip, as they inevitably do during dust storms or equipment malfunctions, the lights dim. Growth slows. Some plants wither entirely, their leaves curling inward as if retreating from an impossible world. And there is another challenge, one that botanists on Earth did not fully anticipate: pollination. On Earth, wind, insects, and gravity work together in an ancient dance that produces fruit and seed. In the sealed environment of a Martian habitat with thin recycled air and no insects, that dance must be performed by human hands. The colonists attempt manual pollination, brushing pollen from flower to flower with delicate tools, but the process is imperfect, time-consuming and exhausting. Many flowers fail to set fruit. The tomatoes that do grow are small, bitter, fewer than needed. By day 78, a new crisis emerges. Several potato plants display signs of disease, dark lesions spreading across their leaves, a rot creeping through the tubers below. On Earth, crop diseases are common, manageable with fungicides, crop rotation, and the resilience of vast agricultural systems. On Mars, there is no backup system. The infection spreads rapidly through the dense planting beds, and within days, an entire section of the potato crop must be destroyed to prevent total loss. The colonists burn the infected plants in the airlock, watching their food supply literally turn to ash. Nutritional deficiencies begin manifesting in the crew with subtle but alarming symptoms. Vitamin D, once abundant through synthesized supplements, is running low. The reserves were calculated based on Earth standard metabolism, but the stress of Martian life, the constant radiation exposure, the psychological strain, the physical demands of working in lower gravity, burns through nutrients faster than predicted. One crew member develops persistent bone pain. Another notices their vision blurring at the edges. These are not catastrophic failures, not yet, but they are warnings. The human body is a complex system that cannot run on inadequate fuel indefinitely. The caloric deficit spiral begins to tighten. As food supplies dwindle, stress increases. Elevated cortisol levels demand more energy. The body's metabolism, sensing scarcity, shifts into conservation mode. But this only makes the crew more fatigued, less efficient at the already exhausting work of maintaining the habitat. Tasks that once took an hour now take 2. Repairs are delayed. Mistakes multiply. The less they eat, the harder survival becomes. And the harder survival becomes, the more calories they desperately need. Water, that most fundamental resource, presents its own cascading crisis. The colony was designed to extract water from Martian ice deposits detected by orbital surveys. The ice is there, buried beneath rust-coloured regolith, waiting to be mined and melted and purified. But extracting it proves far more difficult than Earth simulations suggested. The permafrost is harder, the drilling equipment prone to failure in the extreme cold. The heating systems required to melt the ice consume enormous amounts of power. What was projected to produce 200 litres per day yields barely 50. And every litre of water is contested, needed for drinking, for growing food, for producing oxygen through electrolysis. There is never enough, and the deficit grows daily. Without adequate water, the hydroponic systems suffer. Nutrient solutions become too concentrated, burning delicate roots. Plant growth slows further. The cycle reinforces itself. Less food means weaker bodies. Weaker bodies mean reduced work capacity. Reduced work capacity means less water extracted, and less water means even less food produced. By day 82, rationing becomes unavoidable. The commander gathers the crew and presents the mathematics with brutal honesty. If they maintain current consumption, the food runs out in 12 days. If they reduce intake by 40%, they might stretch supplies for another month, perhaps buying enough time for what? The sentence hangs unfinished in the thin Martian air, because everyone knows the answer. There is no rescue coming. The resupply problem is not one of will, but of physics. Even if Earth launched a supply mission, the moment the Colonies' crisis became known, the journey time is measured in months. The most optimistic trajectory, using the most powerful rockets available, requires at least 7 months to reach Mars. And that assumes a launch window is available, that the mission can be assembled and launched instantly, that nothing goes wrong in transit. The radio signals travelling from Mars to Earth take between 4 and 24 minutes, depending on orbital positions. By the time Earth receives a distress call, processes it, and responds, precious days are lost. By the time a rescue mission could arrive, the colony will have been silent for months. The crew understands this. They understood it before they left Earth. Signed documents acknowledging the risk, accepted that Mars offers no second chances, but understanding a possibility and living its reality are separated by an ocean of denial that only breaks when the food stores are laid out on a table and counted, item by item, meal by meal, day by day. Rationing decisions tear at the social fabric of the crew in ways that no training prepared them for. Who receives full portions? The commander, whose decision-making capacity is essential. The engineer, whose physical work maintains the habitat. The scientist, whose research might provide unexpected solutions. Or equal portions for all, regardless of role, preserving the egalitarian principle even as it ensures everyone weakens at the same rate. Arguments erupt over grams of protein, over whether certain medical conditions justify additional calories. over whether past contributions should be weighed against future utility. These are people who trained together for years, who trusted each other with their lives, who crossed 140 million miles of void as a unified crew. Now they sit across from each other at mealtimes, measuring, calculating, wondering if the person beside them is consuming more than their share. Some suggest drawing lots for who receives reduced rations. Others propose a merit-based system. One crew member quietly begins skipping meals, attempting self-sacrifice that others interpret as manipulation or moral superiority. Trust, that invisible currency more vital than oxygen, begins to erode. On day 85, the agricultural module's main LED array fails, not from age or accident, but from power prioritization. Life support systems are drawing more energy than projected, and difficult choices must be made. The plants are left in darkness for 6 hours before emergency power is rerouted. It is enough time for irreversible damage. Seedlings that were just beginning to sprout will never recover. The food will run out. This is no longer a risk to be managed, but a certainty to be endured. And as the colonists face this reality, they must also confront what comes after hunger, the cascade of failures that will define their final days on a world that was never meant to sustain human life. By day 86, the colony is no longer a daring experiment. It is a machine held together by memory, routine, and the quiet hope that nothing truly important breaks. On paper, each system on Mars looks separate: power, heat, water, air, communications, food production. Life support diagrams show tidy boxes and colored arrows, each with its own backups and redundancies. In reality, these are not boxes. They are threads in a single woven fabric. Pull one, and the others begin to tighten, strain, and finally come apart. This is the domino effect of a frontier outpost. Failure is almost never a single event. It is a sequence. It starts, often, with power. For weeks, fine Martian dust has been coating solar panels, slipping into joints, grinding into hinges. Every sunrise is a little dimmer, not because the star has changed, but because the panels see it through a thicker, redder veil. The crew brushes them off when they can, but dust on Mars is not like dust on Earth. Its particles are tiny, sharp, and cling electrostatically to almost everything they touch. Even small losses in efficiency matter when you live on a narrow margin. Batteries, overworked to make up the shortfall, begin to age faster. They charge less fully, discharge more quickly. An inverter overheats one afternoon and fails with no sound, just a change in numbers on a screen. Power management software starts to make harder choices: what to shut down, what to preserve. Lights dim fractionally. Non-essential experiments are quietly powered off. Greenhouse heaters cycle less often, and temperatures drift a few degrees lower at night. The colony is still functioning, but the energy budget is no longer generous. It is a tightrope walk. On Mars, loss of power is not just an inconvenience. It is a slow rearranging of priorities. Every watt must now justify its existence. Then comes the cold. Martian nights can plunge to negative 80 degrees Fahrenheit, sometimes colder. The thin atmosphere cannot hold heat. Once the sun sets, warmth bleeds into the sky like water spilling from a broken bowl. The habitat's insulation slows the escape, but does not stop it. Only active heating can do that, driven by the same power system now groaning under its own limitations. On one of these nights, a small fault appears in the heating loop. A pump that has been cycling almost constantly for months finally stutters. Bearings worn by dust and vibration seize for just a second. A temperature sensor downstream, already drifted out of perfect calibration by radiation and time, underestimates how quickly the line is cooling. Automatic protections kick in, but a fraction of a degree too late. One zone of the habitat grows colder than expected. A wall cools. A condensation line, never meant to see such low temperatures, begins to freeze internally. Ice forms slowly, invisibly, narrowing the pipe. The crew doesn't notice. They are focused on a different alert. Power demand has spiked as backup heaters try to compensate. Outside, the stars burn with indifferent clarity. Inside, the air is still warm enough to breathe comfortably. Nothing feels urgent, not yet. But the system has started to drift out of balance. Heat pumps draw extra power. Batteries dip deeper into their reserves. To protect core life support, something else is cut. The centrifuge for certain lab equipment, a secondary freezer, a non-critical sensor array. The ship of Theseus transformation continues. This is no longer the same colony that landed on day one. It is a simplified version of itself, pruning away complexity in exchange for survival. And then water notices. The water recycling system is the quiet heart of the colony. Every drop of sweat, every exhaled breath, every used cup is gathered, filtered, distilled, and returned. On Earth, water is a landscape. Rivers, lakes, oceans. On Mars, water is an algorithm, a loop that must never fully open. The partially frozen line in the wall feeds a subsystem in that loop. As ice narrows the pipe, pressure rises. A pump, already near its operational limit, begins to vibrate. Cavitation starts, tiny bubbles collapsing with microscopic violence. The pump still turns, but its efficiency plunges. Flow rate decreases. Inside the control software, numbers shift. Flow anomalies trigger warnings. Filters are getting less input. Tanks are refilling more slowly. At first, the system compensates by lengthening cycles, prioritizing drinking water and oxygen production. Showers, already brief and rationed, become shorter. Some are skipped entirely. The colony begins to smell more like itself, a closed loop growing ever more closed. Water, once an invisible background process, now occupies conscious thought. The crew plans each sip. Then, sometime between days 88 and 90, the pump crosses an invisible threshold, where vibration and time converge. It fails. Suddenly, one entire segment of the water loop goes dark. There is still water in storage tanks. There is still some capacity in secondary lines. But the elegant, nearly closed circuit the engineers designed back on Earth has been broken into islands. The crew can reroute around the failed pump, but every detour costs them pressure, efficiency, and time. More energy is needed to move less water, and power, already compromised, must stretch even thinner. This is where the interdependence reveals its sharp edge. Less power means less heat. Less heat has damaged water infrastructure. Damaged water infrastructure demands more power. The loop closes in the wrong direction. Outside, the planet remains silent. Inside, fans hum a little louder, pumps whir a little longer, and alarms appear more frequently on screens. Each one calls for human attention. Each one steals minutes of sleep. Meanwhile, another quiet failure is unfolding above the habitat, the communication array. From the beginning, a constant stream of data has connected Mars to Earth. Telemetry, health reports, software updates, and the reassuring presence of human voices delayed by minutes, but present nonetheless. The high-gain antenna, is the colony's umbilical cord to a distant parent that can offer guidance, if not immediate rescue. Martian dust, scoured by thin but persistent winds, has been sanding away at exposed surfaces. Connections that were once tight are now subtly loose. A micrometeorite, no larger than a grain of sand, strikes an already stressed component. The damage is almost unnoticeable, a slight misalignment, a tiny crack. Under normal power, stability software could constantly adjust, tweaking the antenna's position to keep it locked onto Earth. But on reduced power, update intervals are lengthened. Corrections are less frequent, less precise. One day, as Mars slowly turns and the geometry between planets shifts, the array drifts a fraction of a degree off target. Bit error rates climb. Packets are lost. Voice calls become choppy, then impossible. Finally, the link drops entirely. On Earth, screens flash, signal lost. Engineers begin running simulations. They send commands, hoping the array will realign. But those commands have nowhere to go. On Mars, the silence is absolute. The crew is not yet doomed. They have supplies. They have knowledge. They have contingency procedures for partial isolation. But something deep in the human brain responds to the sudden absence of the familiar background noise of messages and updates. Isolation, once a psychological challenge, now becomes a technical one as well. They are truly on their own timetable. In a well-stocked workshop, skilled engineers could replace the failed pump, rebuild a damaged antenna actuator, or swap out a burnt power inverter. But frontier colonies cannot bring an entire Earthside warehouse. They bring instead a compromise, a careful selection of critical spares and a 3D printer meant to bridge the gap. The printer can make brackets, housings, simple gears, and custom tools. It can fabricate non-pressurized components and adapters in plastics and some metals. It is a miracle of makeshift manufacturing. But it cannot print high-precision bearings hardened to survive Martian dust. It cannot print radiation-hardened chips, specialized seals, or proprietary micropumps designed in some distant factory. The most fragile, most advanced parts of the colony remain, in effect, irreplaceable. In the planning stages, designers argued over which parts must be redundant, which could be stretched, and which were safe risks. On day 90, those trade-offs are no longer abstract. They are the difference between a fixable fault and a permanent wound. The crew stands at the workbench, laying out disassembled hardware in careful order. They cannibalize one system to save another, stealing components from non-critical instruments to keep life support running. Every choice is a small triage. Every solution creates a new vulnerability. They do all this while exhausted. Sleep on Mars, even in the best of times, is a negotiation between circadian rhythms and a 24-hour, 39-minute day. By day 86, that negotiation is frayed. Alarms interrupt rest cycles. Repair shifts stretch deep into the night. Meals are rushed, eaten standing, tools still in hand. Fatigue narrows attention. Tiny mistakes multiply. A mislabeled cable, a forgotten seal, a bolt torqued slightly too tight, or not enough. In a terrestrial workshop, these errors might be caught and corrected by colleagues, or absorbed by the immense redundancy of Earth's infrastructure. Here, they enter the system like invisible fractures. A tired hand slips while working in a pressure suit, scuffing a connector. A checklist step is skipped to save a few minutes. The team decides to defer a thorough leak test to the next day. They need sleep. Their bodies demand it. The colony, however, does not sleep. Pumps continue to push. Heaters continue to cycle. Fans continue to stir the fragile atmosphere. Every second, the systems that keep humans alive in an alien world are either holding together or drifting further into imbalance. By day 95, the colony is still standing. Air is still breathable. Temperatures are survivable. Water, though rationed, still flows. From the outside, the habitat looks unchanged, a small cluster of modules on a red plain under a pale pink sky. But inside, almost every major system is operating in a degraded state. Power reserves are thin. Heating is compromised. Water recycling is patched and fragile. Communications are intermittent or silent. Spare parts are scattered across workbenches, some repurposed, some irreplaceable. The crew, carrying more strain than any monitor can measure, moves carefully through routines that have become both lifeline and burden. In these days, the colony exists in a delicate equilibrium, like a storm balanced on the edge of a pressure gradient. It could hold, it could fail. The difference may come down to one more fault, one more miscalculation, or one more midnight decision made by someone who has not truly rested in weeks. The countdown to day 100 is no longer just a measure of time. It is a measure of how long a complex, interdependent web of technology and human endurance can stretch before something, somewhere, finally gives way. By the time the calendar flips to day 96, the colony is no longer an experiment. It is a verdict slowly being written in real time. Outside, Mars looks exactly the same as it did on day 1. The sky is still butterscotch. The horizon is still broken only by stone and shadow. The distant hills are still frozen in their silent watching. Nothing in the landscape suggests that inside the thin walls of the habitat, the most difficult decision in the history of space exploration is unfolding. Because for this crew, the journey to Mars was only ever half of the mission. The other half has been waiting in the dust. Parked a few hundred meters from the main habitat sits the return vehicle. To some, it looks like salvation, a slim, upright rocket, bristling with sensors, fuel lines, and the promise of home. To others, it has become something else entirely, a question mark made of metal. Do we dare light this fuse? From the beginning, the plan relied on a quiet miracle, in situ resource utilization, ISRU. Instead of bringing all the fuel from Earth, the colony would make most of it on Mars. Thin air, frozen ground, and a lot of patience turned into liquid methane and liquid oxygen, the propellants that would lift the crew back into orbit and beyond. For months, machines have been humming just outside the hab, pulling carbon dioxide from the atmosphere, splitting water ice from the soil, combining elements molecule by molecule, drop by painstaking drop. Tanks slowly filled while the crew slept, worked, and argued. Every kilogram of propellant was another small vote in favor of a safe return. But on Mars, nothing is guaranteed to keep working. Somewhere between days 70 and 90, the first anomalies began. A compressor cycling harder than expected, a heat exchanger running a few degrees too hot, a valve that no longer fully sealed against the pervasive, electrostatically clingy Martian dust. Small warnings, at first easy to patch, to override, to rationalize. By day 96, the logs tell a different story. The ISRU plant has fallen behind schedule. Sensors show that one of the key subsystems has degraded beyond in situ repair. Even with every workaround, every emergency protocol, the numbers are unforgiving. The fuel tanks are not full enough. On Earth, this is a line in a spreadsheet, a bar on a chart that falls just short of green. On Mars, It is something else. It is the difference between a vehicle that can reach orbit and one that will die in the thin, cold air, falling back toward the planet like a thrown stone. And so the question shifts, not when do we come home, but do we try at all? Complicating everything is time, not just mission time, but human time. 100 Martian days of reduced gravity, limited exercise equipment, borderline nutrition, and constant psychological stress have reshaped their bodies from the inside out. Bones have begun to thin despite resistance workouts. Heart muscles have subtly adapted to weaker gravity. Blood volume has shifted. Some crew members now experience dizziness simply standing up too quickly. Launch is not a gentle departure. Even a modest ascent profile can subject the body to several times Earth's gravity for minutes at a time. In simulations, every member of this crew could handle those loads easily. That was before the chronic low-grade dehydration, before the slight but measurable muscle wasting, before the sleepless weeks wrestling with whether they were going to live or die on a different planet. Now, those same forces that were once routine could be life-threatening. Medical data streams back to Earth. Bone density scans, cardiac telemetry, VO2 max tests on creaking treadmills. Specialists compare them to baseline records with the clinical calm of people who are safe and far away. They model possible outcomes. Who can withstand ascent? Who is on the edge? Who is likely to black out? Who risks cardiac arrest? Behind these numbers are faces, voices they know, people they've trained with, laughed with, fought with. The return vehicle, once a symbol of shared destiny, now raises an unbearable new possibility. It might not be able to carry them all. Even under normal conditions, spacecraft are not generous with mass. Every kilogram of fuel demands more structure, more insulation, more guidance capability. Every additional passenger adds life support, suits, supplies. On Mars, space and fuel are even tighter currencies. With tanks partially filled, there is a new constraint. A lighter vehicle might just make it to orbit if the engines perform perfectly, the guidance is flawless, and the winds at altitude are kind. Add more mass and the probability curve shifts. The margin disappears. If only some can leave, who decides who goes? There are frameworks on paper, ethical guidelines drafted in quiet conference rooms years before anyone stood on Martian soil. Ideas about mission-critical roles, about maximizing survivability, about pre-declared decision hierarchies. But paper ethics are light. They were never weighed against the gravity of looking another human in the eye and telling them they will likely die on this world while you attempt to leave it. The commander feels the double pressure, responsible for every soul in the habitat, and also, by design, one of the people mission planners assumed must survive for the effort to be considered a success. On a whiteboard are sketched options that do not feel like options at all. Send the healthiest and youngest to maximize the odds the species learns something from this. Send those with critical technical skills needed back on Earth. Send those with family waiting. Send a smaller crew to improve the odds of reaching orbit, leaving more behind in the hope of a rescue years in the future. Or send no one and bunker down together. On Earth, in mission control, the debate mirrors and amplifies the one happening on Mars. Rows of screens reflect pale faces lit by data overlays, fuel mass fractions, trajectory windows, physical condition charts, psychological risk assessments. It is a cruel asymmetry. From Earth, they can see almost everything. They can model, simulate, warn, advise. but they cannot touch the valves, cannot feel the stiffness in a crew member's hands, cannot sense the tremor in someone's voice when they say aloud, for the first time, "I don't think I can survive that launch." Delayed by minutes of light time, conversations take on a strange rhythm. A question asked in tears is answered by a calm, rehearsed response, arriving long after the emotion has passed. Mission control is a chorus of experts, but it cannot be what the crew most needs: present. In these final days, time itself fragments. There are long hours of dead silence as the crew disappears into private conversations, into solitary corners of the habitat, into handwritten notes that will never be transmitted. Then there are frenzied bursts, tool checks, suit inspections, final calibration of the ascent vehicle's guidance system, as if preparing for launch might delay the need to decide whether to actually launch. Somewhere on day 98, the decision tree branches. One scenario, they bunker down, they shut down non-essential systems, they cannibalize hardware for parts and shielding, they convert unused rooms into radiation shelters, packing them with water, regolith bricks, anything that can turn lethal galactic cosmic rays into a slower harm. They ration food in ways that would have been unthinkable on day 10. A rescue mission is planned, but even with perfect alignment and flawless engineering, it is years away. Perhaps 3, perhaps 5, perhaps longer. In that version of events, survival becomes less about rockets and more about psychology. Can a small group of humans endure thousands of souls in a metal bubble on a dead world, watching the sun grow and shrink in the pink sky, knowing help is crawling toward them across interplanetary space? Another scenario. They gamble on the sky. They strip the return vehicle to its essentials. Every non-critical kilogram, spare experiments, comfort items, excess, equipment is removed. Seats are examined. Can one be taken out? Could someone lie on the floor, strapped down, to reduce mass and improve center of gravity? They run ascent simulations until the numbers blur, trying to find a corridor between too heavy and too reckless. Perhaps the crew chooses a mixed path. Some stay, betting on long-term survival. Some go, betting on the thin line of mathematics and metallurgy that separates orbit from impact. The final list of who boards the rocket is not announced, but openly lived. There is no ceremony, just quiet, practical preparation, overlaid with heartbreak. Through it all, they keep talking. The last transmissions are not just technical updates. They are recordings of stories, messages to loved ones, reflections on what it felt like to wake up on another planet and realize that the red dust under your boots is older than any mountain on Earth. They describe the way the airlock creaks on cold mornings, how the stars look sharp and too bright in the thin Martian night, how fear and wonder can coexist in the same heartbeat. On Earth, billions of kilometers away, people listen. In living rooms, in classrooms, in crowded bars and silent hospital wards, humanity leans closer to screens, hearing not just the crackle of distant radio, but something older. The sound of a species discovering the edges of its current ability to survive, and pushing anyway. Whether they launch or not, the final hours compress into moments of extraordinary clarity. Checklists are read with steady voices that sometimes catch on individual words. Hugs are exchanged in the clumsy bulk of pressure suits. Someone jokes about the food. Someone else whispers a private prayer. If the engines ignite, the habitat will shudder under the roar as dust explodes outward in a great rust-coloured plume. The rocket will rise, slowly at first, dragging mass and hope into the thin air, fighting gravity and the weight of imperfect propellant calculations. Sensors will track every vibration. On Mars, eyes will strain upward until the vehicle is just a star. On Earth, telemetry will be converted into arcane plots and numbers, watched like vital signs in an intensive care unit. If they choose to stay, there is no roar, just a quiet reconnection of cables, a repressurization of hatches, a return of unused launch suits to storage. The impossible choice is made not with flames, but with stillness. In either path, something profound has already happened. By day 100, the dream of a Mars colony has been stripped of romantic abstraction and revealed as what it truly is. A fragile, lethal, awe-inspiring attempt to step beyond the cradle of Earth. It is not guaranteed. It was never guaranteed. But the willingness to face an impossible choice, to weigh individual lives against knowledge, against the future, against the long arc of a species that has always walked toward the unknown. That willingness is its own kind of success. The first Mars colony might last only 100 days, or 1,000, or it might fail outright in a manner we have not yet imagined. Yet in those last transmissions, in the calm voices detailing system failures and personal fears, there is something more durable than any habitat wall. The quiet resilience of humans who travelled millions of miles, knowing that they might not return, and chose to go anyway. In that sense, the story does not end on day 100. It becomes a beginning written in dust, in data logs, in memories on Earth, waiting for the next crew, the next design, the next attempt to stand once more on that cold, red world and ask, how do we make this time last longer? What does it mean to imagine a colony that lasts only 100 days, not as a failure, not as a disaster movie, but as a rehearsal? In space exploration, worst-case scenarios are not morbid fantasies. They are tools. By walking through the slow unraveling of a Mars outpost day by day, we are doing what engineers, mission planners, and astronauts already do in silence. We are searching for the weak links in a chain that stretches across millions of miles. On Mars, there are no small problems. Every loose bolt, every software glitch, every forgotten backup is a seed that can grow into catastrophe. Thought experiments like this are not predictions. They are lanterns we shine ahead of us on a path no one has walked before. When we imagine life support systems clogging with dust, we are really asking, how many filters, seals, and moving parts can fail before the habitat becomes uninhabitable? When we imagine air turning toxic from leaks or chemical imbalances, we are asking, how often must we test, recalibrate, and cross-check, knowing that the nearest repair shop is a planet away? By playing out these stories in slow motion, we gain something precious. Time. Time to see the failure before it happens. Time to redesign, to reinforce, to rethink. Every hypothetical crisis we solve on paper is one less emergency that must be solved with seconds left on a real countdown clock. Right now, on Earth, the solutions to these 100-day failures are already under construction. In quiet labs and desert test sites, engineers are teaching machines to breathe on Mars. Sabatier reactors turn carbon dioxide and hydrogen into water and methane, sketching the outline of closed-loop life support. Experimental greenhouses coax lettuce and wheat from simulated Martian regolith. testing how much we can rely on local resources instead of endless resupply from Earth. Radiation shielding concepts stack layers of water, polyethylene, and even fungal biomass. Dark, melanin-rich organisms that might one day line the walls of Martian habitats like a living armor against cosmic rays. Dust, that silent saboteur of solar panels and filters, is being studied grain by grain. Engineers are developing electrostatic coatings that repel particles, self-cleaning, surfaces that shake off regolith with tiny vibrations, and seals designed not for months, but for decades of grind and abrasion. Every hinge, every valve, every fan is being asked the same question. Can you survive a world that never rains, where dust never settles, only shifts? Even the air the colonists breathe is being designed for redundancy. Oxygen can be drawn from the Martian atmosphere, split from water ice, stored across multiple tanks and pipelines. No single tank, no single compressor, no single algorithm is allowed to become the single point of failure. The lesson from our imagined 100-day colony is simple but unforgiving. If one break can end everything, the design is not finished. Mars does not reward minimalism. It demands excess. On Earth, we celebrate efficiency, doing more with less. On Mars, survival may mean the opposite, doing less with more. More spare parts, more backup systems, more power than we think we'll need, more food, more water, more margin for error than looks reasonable on a spreadsheet. Redundancy is not an indulgence in space. It is a philosophy. Every critical system on a Mars base will likely exist in multiples. At least 2, often 3, sometimes more. 2 independent ways to make oxygen. Separate loops for water recycling. Parallel computer systems that can take over if one fails or is damaged by radiation. Cables laid along different paths so that a single micrometeorite or a single fire cannot sever all communication to orbit. We call this over-engineering, but in truth, it is simply engineering scaled to the reality of Mars. A reality where a bad sensor reading can lead to a wrong decision. Where "we'll fix it next week" becomes "we may never fix it at all." Over-engineering is how we trade mass and complexity for something far more valuable. Time to respond when the unexpected happens. And the unexpected will happen. Behind the romance of the first bootsteps and flags, there is another truth. Mars colonization is not a single mission. It is a multi-generational project. The first crews will not be settlers in the traditional sense. They will be builders of infrastructure, testers of systems, cartographers of risk. Their job will not be to create a perfect city on Mars. Their job will be to make the next mission easier, safer, and more informed than their own. The timeline to a self-sustaining Martian civilization is not measured in launch windows, but in lifetimes. We may see the first human footprints in one generation, the first semi-permanent bases in the next, and true cities, if they come at all, only after many cycles of trial, error, and redesign. It took thousands of years for humanity to adapt fully to every extreme environment on Earth, from polar ice to high mountain plateaus. Mars will not accelerate that process. It will amplify it. Yet we are already rehearsing for this long story in small, imperfect theaters on Earth. In the deserts of Utah, at the Mars Desert Research Station, crews live for weeks in a cylindrical habitat, donning simulated spacesuits every time they step outside. They learn how small delays in communication affect decision-making, how quickly chores pile up when everything must be done through layers of protocol and protection. In Hawaii, at HICs, volunteers spend months in isolation on the slopes of a volcano, looking out at black lava that stands in for Martian basalt. There, the experiments are not just about hardware, but about humans, how they cope with confinement, conflict, monotony, and the subtle erosion of privacy. These analog missions do not capture everything. Earth's gravity, Earth's air, and the knowledge that a hospital is only hours away always sit in the background like a safety net. But within those limits, we learn. We learn which tasks drain the crew emotionally, which schedules lead to burnout, which leadership styles help a small group remain a team instead of fracturing into cliques and quiet resentments. On isolated research stations in Antarctica, in submarines beneath the sea, and on the International Space Station orbiting above our heads, we are studying the same question from different angles. What does it truly take to live, not just survive, in a hostile place for a very long time? Every frustration logged in a mission diary, every simulated emergency that goes wrong before it goes right, feeds back into the design of real habitats, real procedures, real training. Our imagined 100-day collapse becomes, in this way, a map of where we must reinforce the bridge before anyone tries to cross it. If this all sounds daunting, that is because it is. But difficulty does not mean impossibility. The story of human spaceflight has always been written along the edge of what we thought we could do. At one time, staying alive in orbit for a single day seemed ambitious, then a week, then a month. Today, astronauts live continuously on the ISS for 6 months or more, relying on complex, imperfect, constantly repaired life support systems. Every leak, every failure, every improvised patch on the station's plumbing and wiring is a small rehearsal for Mars. The challenges we have explored in this thought experiment: dust that chokes machines, air that can turn deadly, radiation that quietly rewrites DNA, minds strained by isolation, food stocks dwindling, systems failing in sequence, are not reasons to turn back. They are reasons to prepare differently. Understanding how a Mars colony might die is how we learn to help it live. Failure analysis is not pessimism. It is respect. Respect for an environment that will not bend to our needs. Respect for the limits of our current technology. And respect for the lives of the people who will one day trust that technology far away from home. When we look honestly at the 100-day horizon and see all the ways things can go wrong, we are not closing a door on Mars. We are opening a clearer one, a door framed by backup systems, tested procedures, hardened materials, smarter software, and humans trained not just to operate a habitat, but to understand it at a fundamental level. The future of humanity on Mars will not be secured by bravado or by blind optimism. It will be secured by patience, by iteration, and by the humility to imagine failure in enough detail that we can design our way beyond it. In that sense, the first colony that only lasts 100 days might be more valuable than the one that lasts 10,000. Because in its short, fragile existence, whether real or imagined, it teaches us the lesson at the heart of every great exploration. We do not earn new worlds by pretending they are safe. We earn them by learning exactly how they are not, and choosing to go anyway. As our 100 days on Mars come to an end, the colony falls quiet. Airlocks that once cycled with the rhythm of human routine are still. The green of the hydroponic trays has faded. The hum of life support has been replaced by a thin, unbroken silence. From orbit, the habitat is no more than a small geometric blemish on a rust-red world. A brief sentence written against a planet that has been telling its own story for billions of years. In one sense, this is a tragedy. Machines have failed. Systems have broken down. Human bodies and minds have been pushed beyond limits they were never designed to meet. The dust, the radiation, the isolation, the scarcity, all of it has conspired against a fragile experiment in survival. Mars does not rage like Jupiter, but it resists us in quieter, more patient ways. It erodes seals. It corrupts circuits. It waits. And yet, in another sense, the attempt itself is an extraordinary success. Because those footprints in the regolith, those first struggling green leaves in a Martian greenhouse, those handwritten notes in a mission log, they are proof that a species born in one thin band of atmosphere around a single small world refused to stay there. In a universe where most planets will never know they exist, humans chose to step onto another one and try. We often imagine exploration as conquest, as planting flags and claiming territories. But the reality looks more like this: prototypes that fail, habitats that don't last, missions that end before we want them to. Progress is not a straight line. It is a series of fragile experiments stacked on top of each other, each one barely standing long enough for the next to be built. The first Mars colony might last only 100 days. The second might last 200. The third might survive a dust storm but fall to a subtle flaw in radiation shielding. Each attempt writes new data into our understanding about how long materials endure in Martian dust, how minds adapt to red horizons, how food systems bend and break under real alien gravity instead of simulations on Earth. In that way, every failure is less an ending and, more a relay handoff, a passing of experience forward through time. The colonists who do not make it to year 1 may still be the reason another crew someday sees year 10. We measure their achievement not only in days survived, but in the knowledge that outlives them. Human history is full of frontier towns that vanished, failed settlements reclaimed by forests, collapsed expeditions remembered only through journals and rusting tools. Yet over centuries, the map filled in. Coasts became continents. Unknown oceans became familiar routes. What feels like catastrophe in the moment becomes, with distance, the necessary price of learning. Mars will likely follow the same pattern. At first, we will send small, precarious outposts that seem to crumble under the slightest pressure. Over time, we will return with better shielding, smarter software, hardier crops, and more honest expectations of what this world demands. The first colony may fail, but it will not be the last. The long view stretches beyond a single mission, beyond a single lifetime, into a chain of attempts that, taken together, become a civilization learning how to live on more than one world. As you drift towards sleep, perhaps imagine that distant future. Children who have never seen an open blue sky, who learn about Earth the way we learn about ancient oceans on other worlds. Cities carved into cliffs, lit from within, trains that cross crater rims, gardens growing under a sun that shines smaller but no less precious. Before you go, if this journey through the first 100 days on Mars kept your mind company tonight, you can gently tap like and let the algorithm know this is a story worth telling again. In the comments, share where you're listening from. What planet, what country, what quiet room becomes a temporary capsule as you drift towards sleep? If you'd like more voyages like this, consider subscribing so you don't miss the next expedition. And for those who want to support this channel a little more deeply, there is an optional YouTube membership, never required, but always appreciated. It helps us keep exploring these long, slow questions about time, space, and the fragile persistence of human dreams. For now, let Mars recede into the darkness. The first colony's lights have gone out, but somewhere plans are already being drawn for the next launch window. In the long view, this is not the end of the story. It is only the first chapter.